we just concluded that this part of the equation must be some constant, which we called lambda. And therefore, the angular part, which we wrote in terms of a function y, must be negative lambda. So this whole thing now let's assume separability in this function as well, and then the general solution can be built up from those solutions. So capital Y is equal to some part that is only a function of theta, we'll call it capital theta, and a part that's only a function of phi, we'll call that big phi. And we can do something similar to what we did before, which is to put this function into here and then try to separate out the two parts. And so if we put this function to here, we will have 1 over capital theta, capital phi, times 2 derivatives in theta of this function. So it operates on this part. So this part goes along for the ride. Maybe we should write this as that way, so that the variables phi and theta make a little extension here compared to this. So let's turn this into this. Here we have this just going along for the ride, and then we have 2 derivatives in this, in that variable, plus that going along for the ride here, cotangent of that, derivative of this in that variable, plus capital theta function. So here it's this part that goes along for the ride. We're dividing by the same thing there, because we have it here, and this capital phi function. Then we have this sine squared of theta, and we already took this part out of this, and so all we have left is the, it's not a partial anymore, it's just 2 derivatives in that function in phi, and this must be that. So we have a theta part here, but we want to try to bring all of the theta parts over here, and so we can rewrite this and simplify. We can cancel here, we can cancel here. We end up with sine squared theta over capital theta, 2 derivatives of capital theta in theta, plus sine squared theta, cotangent of theta over capital theta d capital theta d theta plus 1 over capital phi, two derivatives of capital phi and phi. And that has to be minus lambda times sine squared of the theta variable. So what we have here, as theta varies, this varies. As theta varies, these two terms can vary, can change. But this is only a function of, this is at most only a function of this. And so if phi is changing, this term must be, since it's at most a function of phi, it must actually not even be a function of phi. It must just be a constant. So that means that we have something like 1 over this function, capital phi, second derivative of this in phi is equal to some quantity. Doesn't really matter what we can make it a little bit trickier for ourselves, but we can make it a negative. Let's make it a quantity that's positive and put a minus sign there, and then we'll end up at the same place even if we don't do that kind of thing. But normally it's written in terms of this function m, and so this leads us to the solution of this function being some coefficient. These are the exponential functions with m, I to the m phi plus b e to the minus I m phi. And so m in general can be complex, but we notice that phi plus 2 phi is the same location as phi, right? We're just dealing with the angle phi. And so phi, let's, how do we say this? Capital phi of that must be equal to, well, it's capital phi of phi. And so we can say that e to the I m phi plus 2 phi is equal to e to the I m phi. And so e to the 2 pi I m is equal to 1. So it looks like that, and what follows from that is that m is equal to 0. It can be 1 or negative 1, so plus or minus 1. It can be plus or minus 2, and so on. So these are integers, and so the general solution has this radial part that's a function only of r, has this theta part. We don't know what these two are, but we've figured out what this phi part is capital phi, and it looks like this. So the solutions have that form. Well, I should say that psi proportional to these functions.